Good day, everybody. I am Jinzhang Liu from National Zhongzheng University, Taiwan. Now we will present our paper entitled Low-Light Image Enhancement Using Autoencoder-Based Deep Neural Network. This is the outline of our presentation. First, we will give a brief introduction. Then we will describe our proposed approach. Then we will show some experimental results, followed by concluding remark. One of the research issue in image and computer vision application is low-light image enhancement. Three main categories of low-light image enhancement approach, including enhancement-based, illumination-based, and learning-based. For enhancement-based approach, histogram iteration and gamma correction are usually used to adjust the dynamic range of image pixels. For illumination-based approach, by Rectangel's theorem, each image is decomposed into reflection and illumination component for further processing. In this study, a low-light image enhancement approach using autoencoder-based deep neural net is proposed. This is the framework of the proposed approach. It is autoencoder-based deep neural net. The proposed approach consists of two subnets, namely feature extraction subnet and the color enhancement subnet. FE subnet extract image feature from the low-light image and enhance detailed texture. While CE subnet recover the color information of the low-light image and perform image denoising. Finally, the processing result of FE and CE subnet are fused to generate the final enhanced image. As shown in Figure 2, FE subnet consists of an encoder and a decoder, in which butternet guided channel attention module BGCA can effectively enhance image detail and image textures. As shown in Figure 3, butternet guided channel attention module uses the network's butternet one-by-one convolution structure to reduce the amount of computation. BGCA1 and BGCA2 in Figure 1 will separately operate with different global averaging pooling. Note that BCCA with different size will generate the corresponding FBCZA with different size. As shown in Figure 4, color enhancement subnet consists of RZHS relative global histogram strengthening module and denoising module. In this study, the proposed RZHS module is first performed in RGB color space and then is performed again in the CIELAB color space. The proposed RZHS module can improve image quality by global histogram shading, enhancement color saturation due to low-light image characteristic, and retained image detail and textures. As shown in Figure 5, in this study, the proposed denoising module consists of 8 consecutive direct convolution followed by renew activation function and one direct convolution followed by signal activation functions. For autoencoder architecture, different convolution and pooling operations with image downsampling and receptive field enlargement are performed at the encoder. Thus, some information may be lost. To couple with the above problem, direct convolution and skip connection are employed in this study to expand receptive field and maintain image resolutions. In this study, mean square error, MSE, and structural similarity index structure measure SSIM are employed as loss function. The total loss function is defined as equation 1. And in this study, adaptive moment estimation optimizer or ADAM is employed. For experimental result, two datasets LOS and LSRW are employed, and two objective metrics PSNR in DB and SSIM are employed. In terms of average PSNR and the SSIM, performance comparison between 5 comparison approach and the proposed approach on LO dataset are shown in Table 1. In terms of average PSNR and the SSIM, performance comparison between 5 comparison approach and the proposed approach on LSRW dataset are shown in Table 2. Figure 6 shows some experimental results on LO dataset. Part A through H show include low-light image ground truth process image by 5 comparison approach and the proposed approach, respectively. Figures 7 shows some experimental result on LO dataset. Image A through H show the low light image ground truth 5 process image by 5 comparison approach and the proposed approach. Image I through image P shows some corresponding detailed part of image A through H. Figure 8 shows some experimental result on LSRW dataset. Image A through H show the low light image ground truth 5 process image by 5 comparison approach and the proposed approach, respectively. Image I through image P shows some corresponding detailed part of image A through image H. Concluding remark. In this study, a low-light image enhancement approach using autoencoder-based deep neural net is proposed. Based on the experimental results obtained in this study, in terms of two objective performance metrics and subjective evaluation, the performance of the proposed approach is better than those of 5 comparison approaches. This is the end of my presentation. Thank you for your attention. Thank you.